We've recently started talking about some segments in triangles. We started talking about the mid-segment, and today and in our next couple of classes we'll start talking about some other segments in triangles, and we're going to start with perpendicular bisectors and angle bisectors. So perpendicular bisectors and angle bisectors. So we've talked about these before, and this time we're talking specifically about in triangles because we're going to use these when we start talking about concurrency. The first thing we're going to talk about is the perpendicular bisector theorem. The perpendicular bisector theorem states if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So here we have segment AB, which is drawn, and CD, which is the perpendicular bisector. So that means that that's congruent to that, and that right angles are formed. Well, of course, you remember that we can't just use something, we have to prove it. So let's do that. So let's go about proving the perpendicular bisector theorem. So we're given that CD, line CD, is perpendicular to segment AB, and line CD bisects segment AB. And we are asked to prove that DA is congruent to DB. So let's put those into our diagram. And let's change our color. Okay, so DA is congruent to DB. Okay, so just like we did before, if you feel very confident, you remember how to do proofs and you feel good, pause your video now, do the proof, and check back in a minute. Okay, so let's do some statements and reasons. And we'll start with one of our two given pieces of information. So I'll start with CD, line CD bisects AB, segment AB. And our reason for that is that it's given. Okay. And because it's given and that it bisects, I can say that AC is going to be congruent to BC. Put that into our diagram, and our reason is going to be definition of segment bisector. Okay. And now I've done everything that I can with that, so let's use our other given. CD is perpendicular to AB, which is another given. Okay. And as soon as I see that perpendicular symbol, that says to me something about those angles. Okay, so it tells me that angle ACD and angle BCD are right angles. By definition of perpendicular lines. Okay, perpendicular lines form right angles. And from here, that tells me that angle ACD is congruent to angle BCD because all right angles are congruent. Okay, so now I've got a side and an angle. And remember, we always try to look for the easiest. And when I look back at my diagram, I notice, hey, right here, we share a side, so I can use that reflexive. Remember, we're always going to try to look for those things that are easier to use than other things. So we've got that DC, segment DC, is congruent to segment DC. And for 6, it's the reflexive. Okay. And now, hey, wait a second, we have two triangles that are congruent. Triangle ACD is congruent to triangle BCD by side angle side. Now remember, that's not what we were trying to prove. We were trying to prove that DA is congruent to DB. So we need one more step. DA is congruent to DB. Our favorite 5 letters, CPCTC. Corresponding parts of congruent triangles are congruent. So now that we've proved the perpendicular bisector theorem, we can use it. You're probably wondering, how would we use this? Well, I'll give you a very quick example. If we had a triangle and we are told that in this triangle, that's congruent to that, and I'm told that this, if I tell you the length of, I'll make this A, B, C, D, if I tell you that AD is congruent to CD, and I tell you that BC is 15, well then you should be able to tell me that BA is also 15. That's a very quick example. Of course, they could get more challenging than that. Might involve some algebra or overlapping things, but that's basically what we would use this for on the most basic level. But wait, there's more. Don't go away. We also have the converse of the perpendicular bisector theorem. The converse of the perpendicular bisector theorem states that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So just a quick, what that would look like is if I have a segment, AB, and I have a point C, such that if I draw a line from a segment from C to A and C to B, and they're equidistant, then that means that there's some imaginary line that's drawn through C that is the perpendicular bisector. And this works for any point C on the segment there. I could put my C anywhere on that line, and anywhere we would end up with these things being equal distance so long as they are truly on the perpendicular bisector. Now it gets a little bit crazy here with all these overlapping lines. Let's do one more. Let's do the yellow one. Okay. So as long as each of these are equidistant, then those points would be on the perpendicular bisector. The good news is that you will prove this, but you'll be doing it on your own. Please note that you are responsible for drawing all diagrams. That may be one diagram from multiple questions, and completing the proof in number 41 completely.